Welcome back, students. Today we're going to be doing Lab 2, the scale of the universe. And what today's lab is meant to do is to provide you with an idea of how big things are in the universe. So starting with things that you should be somewhat familiar with, the size of the Earth, and about how far away the Earth is from the Sun, and how long light takes to travel those distances, on to larger and larger scales. So not only Earth, but Earth and the inner planets, and then the whole solar system, and then where the solar system is with respect to the stars closest to our sun. And then after that, zooming out to even more stars, eventually the size of the galaxy, and zooming out from that into the local group of galaxies to get a scale for how big the universe is. So when you go through the lab, there will be animations showing a zoom out basically for these scales, so we don't really need to cover that in the introduction. The introduction is mostly going to be about the mathematics and the conversions you'll need to be doing in order to make sense and actually come out of this lab with numbers to put on the general feelings of how you should see some of these objects. So the first thing we're going to need to do is know how to interpret a graph. So in most of the steps of this lab, once the animations stop, you'll be left with a screen similar to this, some sort of grid pattern, and then a number for the width of the view. And I believe the width and the height is the same, even if the grids don't appear to show that. So one thing to keep note of is the grids I have here are not going to be the same as the grids you'll have. This one is 1, 2, 3, 4, 5, 6, 7 grids across and 7 grids vertically. And I'll also refer to these grids as boxes on and off. So each box horizontally is what we'll mainly be counting, and then every once in a while we'll also count the vertical boxes as well. So if I say one box length, that is from here to here. It's across a box. So if we were to split this 25 feet up, 25 is from the left wall to the right wall, each box would be 1/7 of 25 feet. Now I purposefully made these numbers not comfortable to divide into one another so that you can't use tricks. For example, if there were only 5 boxes wide and the view was 25 feet, we would know that each box is 5 feet. So I've done that on purpose just to make it a bit harder and a little bit less easy to use mental math. Because in the lab today, the numbers will be quite complex, usually. So it will be harder to use mental math for anything like this. And then some questions you'll get asked are basically, what is the distance from one object to another object? So for here, it is how many feet away from the left wall is the red dot. So here's the red dot, and we can count the number of boxes from the left wall, 1, 2, 3, 4, and then 4.5 about. It might not be exactly on the halfway mark, but it's definitely close enough for us to call it 4.5 boxes. So 4.5 grid spaces from the left wall, but that doesn't really give us our answer. We're looking for how many feet away from the left wall is the red dot. Luckily, we know the two things we need. We have the total width of this, and we have the number of boxes horizontally across here. So what we can do is plug these into an equation, and since we know we want to end up with feet, and we want to get rid of grid spaces, I've plugged them in such a way that if we were to cancel out the values, so we would cancel out this grid spaces, and also cancel out the divide the number through, we would be left with feet and not grid spaces. So what I did is I started with the number that we just measured, 4.5 grid spaces, and then I know that the entire width is 25 feet broken up into 7 grid spaces. So what I did is put the 7 grid spaces on the bottom. That allows me to cancel the grid spaces out, and our answer will be left with a label of only feet. And if we do that math, we are left with 16.07 feet. All right, so 16.07 feet is the answer for how many feet away from the left wall is the green, or is the red dot. Another way you could do it, and this is the way I will do it during most of today's actual lab, is to just put the fraction of the total grid spaces in one fraction here. So we have our 4.5 grid spaces, and that's divided by the total number of grid spaces. So if we were to just divide this, we would have the fraction from the left wall of the entire width. And then multiplying that by the 25 feet is the fraction of the total distance from the left wall that we're actually measuring to our red dot here. So it's the same math. Again, see that the 7 grid spaces is on the bottom, whether it's on the right side or the left side. If we were to cancel this out, the grid spaces would cancel with the grid spaces, and we'd be left with an answer that's in feet, and it is the same answer. So we could do these for different measurements. We could measure how far from the right wall, so 2.5 boxes divided by 7 grid spaces times 25 feet, and that gives 8.93 feet. So you can see that it is a very similar calculation. All I had to change was the number of grid spaces. So if you do get this set up on a calculator or on some sort of online mathematical calculator, or even on Excel or some spreadsheet program, it is as easy as just changing a number here or a number there. So what you need to keep an eye on is your length that you measure, how many grid spaces or how many boxes. The total number, which won't change during today's lab, but it will not be 7 for you guys, and the total width of your view. So that will change every time the camera zooms out from an object. All right, and then moving forward into converting to different lengths. So now we know how many feet that is away. It's 8.93 feet from the right wall. If we wanted to convert to inches, we could do that. Basically, once we have this answer, we again want to cancel out the units. So we have an answer in feet. We want it to be in inches. So we know that there are 12 inches in each 1 foot. So we do this math here. Basically, we multiply 8.93 times 12 and then divide by 1, and that gives us 107.14 inches. And if we wanted to do this some other way, basically all you need to do is make sure what you want to get rid of. So in this case, feet has the number you started with, and then in the divisor somewhere, that label gets canceled out. So this is a very useful tool in physics and many of the other sciences as well. If you know what you're trying to get your answer, and all you need is some conversion. So 12 inches in 1 foot, or if you're going the other way, it is 1/12 of a foot per inch. And after you divide those feet out, they cancel, and you're left with your answer in inches. So now we know how to convert distances on our graph to distances in real life using the width of the view. But so far all we've covered is if we have 2 points that are perpendicular to one another or along a straight line. You will be asked a question similar to this, basically where 2 dots are at some sort of angle from one another, or 2 things we're trying to look at are at some distance that is not clearly defined on the grid lines. So one way you could solve this, it's probably just more of an estimation way than to actually solving this distance, is to place a ruler on your screen, measure this distance, and then measure that same distance in grid boxes from one of the walls. You could do that. I would advise not to do that just because the view should be the same vertically and horizontally, but normally you'll be given a view that is stretched in one direction, and that could throw off your results. So like we see here, the boxes are longer horizontally than they are vertically, and they should be the same width because it's the same number of boxes, and it should be the same 25 feet vertically and 25 feet horizontally. However, if you do have a situation where you're pretty sure that your view is the same, everything is square, placing a ruler or anything you can use to measure on the screen, just measuring this distance here and then measuring that same distance in boxes and converting the boxes to feet like we've been doing could be a valid solution. What we'll be doing here is the mathematical way of solving this. So what we want to do is make a right triangle. And if we know the two sides of our right triangle, the A and the B, we'll be able to figure out the C. And the C is the important one that we need. It's the hypotenuse. So just looking at the screen, we can measure A and B quite easily. A starts about halfway up and it ends about halfway up. So it is about 1, 2, 3 boxes long. And B is 1, 2, 2.5 boxes across. We can plug that into this equation here. So we can plug those into this equation here. C equals 3 squared plus 2.5 squared, and the answer we get from that will be the length of C, or the length between these 2 points. So even though they don't fall on a grid line, we can find that by measuring straight along the grid lines and getting very accurate measurements. Once we have this, we can convert it however we want, so we can convert it to inches or feet the way we did in the last few slides. So we treat this, whatever this number is, in boxes, just like we would treat a number that we measured ourselves. So now we're going to move on to learning about 2 more units of distance, one that you probably covered in class already, and then this one here, the light second, which doesn't come up as much in class, but it is also quite useful. So a light second is just what it sounds like. It's the unit of distance equal to the distance light can travel in the vacuum of space in 1 second. So how far light travels in 1 second. That number specifically is 299,792 kilometers. And if we are to just round this a very little bit, it is 3 times 10 to the 5th kilometers. This E here means times 10 to the power of, so 3E5 is the same as 3 times 10 to the power of 5. So light travels very, very far in 1 second. Light is very fast, is what you should take away from that. And then in the exercise, you'll be given questions like this. How many seconds does it take light to cover a certain distance? Or how long does it take light to travel a certain distance? And in this case, the distance is 4.5 times 10 to the 10 kilometers. So what we do is we set up our equation. This is the number we're given, 4.5 times 10 to the 10, and then we plug in our equation here. Now I know that we want our answer in seconds, so I've made sure to set it up so that kilometers in our starting value will cancel with kilometers in our conversion, and seconds will be the only remaining unit after all the cancellation is done. After that, I can do the math. I multiply this by 1 second and divide by this number here, and I get 133,425.8 seconds. So that is how long it takes light to travel this distance here. And you could convert that to other things if you wanted to, minutes, days, hours, really anything from there. The last distance we're going to cover is the light year, and this is probably the one you're more familiar with from class or even just hearing about distances in space up to this point. So a light year is, again, the unit of distance equal to the distance light can travel in the vacuum of space in 1 year. And the number on that is 9.46 trillion kilometers, or 9.46 times 10 to the 12 kilometers, which is the much easier way to write it. And now that we can see this number here with all these zeros, we can start to see why first scientists tend to use scientific notation, because keeping track of all these numbers to the right of 9 can get quite hard. So this is a much easier number to keep track of than this number here, and why we would want to convert the larger distances to light years. So for example, the closest stars to our sun are about 4 light years away. If we were to measure that in kilometers, it would be somewhere on the order of 36 trillion kilometers away. And just keeping track of all of those zeros, even with scientific notation, can get quite old. So instead we say about 4 light years, and it's much easier to have some sort of an idea how far that is. Again, we'll get questions. How many light years is this number here? The same number from the last question. And we'll plug it into our equation here. So kilometers, again, will cancel with kilometers. Our conversion here is 9.46 times 10 to the 12 kilometers in 1 light year. And that gives us an answer of 0.0042 light years. So this number here is quite a bit less than 1 light year. What we could also do is rephrase this question. So instead of asking how many light years is this distance, we could ask how many years will it take light to travel this distance. And everything would be set up the exact same way. Kilometers would be in our original number here. We would set it up so that we have 9.46 times 10 to the 12 kilometers down here, except this would just be 1 year. So light can travel this distance in 1 year. We would leave the light part out of it. And after we do our math, we would get the same answer, except this answer would now just be 0.042 years. So how long does it take light to travel this distance? 0.042 years. And that is a small amount of time. I believe it's less than a day. So you can use that to compare to how far light travels in a year, how far away to the closest stars, or to some of the things you'll be doing in the class today, comparing it to how long light takes to travel within our solar system or across the galaxy. So this should be all you need today to do the exercises in the lab. Again, most of it is just watching as you're moving from one object to the next or one system to the next, seeing things that you know, starting with the Earth and comparing that to the inner solar system, comparing our place in the inner solar system to the outer solar system, and then moving to the local stars, the galaxy, the local group of galaxies, and the universe, and keeping track and mostly just trying to get a good idea in your mind of the relative sizes of these things. So most of the time we're moving several orders of magnitude, so just comparing the size, but knowing that one thing is a lot bigger than another thing can really be helpful, and hopefully that's what you'll come out of today's lab with.